Hi, welcome to MEN 221 and today we are going to talk about distributed loads and what it is, how are we going to use it, how do we find the information that we want, how we're going to represent it and all of that. So let's get started. Okay, so what are we learning in this session? So first thing we're going to talk about is what is a distributed load and why should we care? Okay, so that's item one. How do we describe them? So what is a mathematical way of describing distributed forces? And what's a systematic way to compute the net force and net moment due to distributed force? Well, why do I care about net force and net moment? Remember, when I have to do equilibrium, I have to find out net force, net moment, okay? And then, how do you use a shortcut for commonly occurring cases? You know, if you do a systematic complete version, sometimes the calculations will get kind of long because you have to do some integration and so on. But for common cases, there's a shortcut that you can do which will help you a lot. Okay, so let's get started. So first question, what is a distributed load? If you looked at our problems up to now, we have always had loads which were concentrated. What I mean by that is we had loads which were focused on only one point, and basically we knew the total force, say 600 pounds, and where it was applied. Okay, and the units for that was pounds or Newton. That's what we did, right? This is a typical example. But in many situations, that's not happens. For example, wind loads on a building or wind loads on something. So for example, if you look here, if you are near the ocean, you will not get a single point load. What you will get is a load spread over a huge area. Okay, the load at any particular point will be very small, negligible actually, but it will add up. So think about it this way, wind is not, even if it's a hurricane, the force of the wind is not that high compared to say a bullet or something like that, right? But because it acts over a wide area, it can have devastating effect. So we have to be prepared for that. And in fact, this is the same thing if you're doing an oil rig, for example. Underwater, the forces due to the water current will be very, very large, and you have to account for it. And it's not acting at just one point. It's distributed all over the place. That's why we care about it. Skyscrapers, for example, are built with distributed loads. If you are interested, you should look at what happened to the City Core building in New York City. So go type City Core distributed load on Google, and you will learn a lot about how important wind loads were for that building and how close to actually completely collapsing it came. So go take a look at it. It's a very fascinating study. Okay, very good. So we now know that distributed load means load at any point is very, very small, but it is spread over a huge area, and the unit for a distributed load is usually what you call pressure. So when you hear about water pressure or something like that, we're talking about a distributed load. But pressure is only one kind of distributed load. There could be others. And the unit in 3 dimensions for this will be Newton per meter squared, or PSI, pounds per square inch. And in 2 dimensions, it will be Newton per meter, or pounds per foot, or pounds per inch. So notice the difference in the units between this and that. Okay, very good. So now let's talk about how are we going to represent it. So if you have a concentrated load, what you do is you can represent it pretty simply. You can represent it as force at particular locations. So in this particular case, you have a 400 pound force at 0, and then 800 pound force at 3 feet, and then 800 pound force at 6 feet, like that, right? So it tells you where the force is and how much it is. You can actually write it if you are used to what is called the Dirac delta notation, and if you are used to a Dirac, technically what's called a Dirac delta distribution, you can rewrite it. So delta x minus x naught means 1 unit at x naught. That's the meaning of this Dirac delta. So now you have 400 units at x minus 0, which is written as delta x, 800 units at x minus 3, which is x equal to 3 is when the force is, and then 800 units at x equal to 6. I'm just this is not that important at this stage, but I'm just showing you that even concentrated loads, you can write it in some kind of a notation. What do you do with the distributed load? Now look at this one. Notice that the load is distributed over the whole beam. It's like a sinusoidal distribution. And if you look at the load at any particular instant, this is not the load, it's the load intensity. How hard am I pushing at that point? It's a load intensity. Okay, and it's given by, as a function, W of x, and its unit will be Newton per meter. So in this particular case, W of x looks like sine pi x over 2L. This is the counterpart to this kind of thing. And since it's distributed, every value of x is allowed. Here only distinct values of x are allowed. You see what I mean? There every value of x is allowed. That's how distributed loads are described. Very good. So now, you know, when you're interested in figuring out what are the forces at the joints because of this distributed load, suppose I want to find out what's the effect here or what's the effect here, I need to find out how much force am I applying and how much moment I'm applying. So how do I do this? Now calculus to the rescue. Okay, so this is where we are going to use our calculus skills. So first item, here's some distributed load. You can see that it is distributed according to something. Wx is the load intensity. Df is the incremental load in this region, which is equal to W of x dx. That's how much load is acting per small region. And the smaller the region, the smaller the force. But what happens is the net force will add up. It's the sum of all of this. So first item is the net force is the sum of all the elemental forces. So which is integral from A to B. So if this is A, if this is A and that's B, then it is the integral from A to B of that, which is this net area. So if you want to find the net force, you have to find the net area under the graph. And net area under the graph, you know, is an integral, right? So the net force due to a distributed force is equal to the area under the graph. The net moment looks like some x minus xp times, if I want to find the moment, let's say at this point xp. Then I do x minus xp times df, which is x minus xp times wx dx. So this is the incremental force. This is the moment due to that force, and it's the first moment of the distribution. Now you're thinking, okay, I gotta do some integrals and all of this stuff. Yes, welcome to why we learn integral and differential calculus. So here is a chance for you to look at integrals. It turns out this is equal to the net force times the distance to the centroid of the force distribution. So if you want to figure out where the centroid is, then it will be equal to the net force times the centroid. How far is this? So what we are going to do is we are going to take a distributed force like that and replace it with an equivalent concentrated load F total acting at the centroid. So where it acts, the equivalent load where it acts is called the line of action. This line of action, and you obtain that by calculating the centroid. And you're wondering, hey, you know what, this looks familiar, right? You know, this is what we did for gravity. So when we looked at gravity, if I look at a lump and I looked at the force of gravity, gravity is pulling for every point in the body. So it's a distributed load. We replaced it with a single load at the centroid of the body. That's exactly what we can do to any distributed load. All distributed loads are like gravity. You have to find the centroid and stick it up there. Okay, that's how it works. Got it? Very good. Now let's try first example. Here's a very simple one. I got a big like a frame on which some bricks are sitting. Each brick dimension is given, and it turns out that it corresponds to a distributed load of 300 Newton per meter over a length of 1.4 meters. This point is A, this point is B. Here is my x component, here is my y coordinate, and our question is, what is the force on this? So how do I do that? First step, This is our systematic approach. This will always work. Step 1, write the force function. In our case, that looks like W of x equals, it's a constant function, no? You can see it's constant and its value is 300. So it is 340 Newton per meter. Hey, that was easy. In other cases, in this particular case, it's not a function of x. So that's very nice. So now we want to find out F total equals integral A starts out at 0, B is at 1.4 of W of x dx, which is integral 340 dx from 0 to 1.4, which turns out to be 476 newtons, which is equal to the area under this graph. 340 times 1.4. Very good. How about the moment? Integral, I'm going to calculate moment around A. So it's x minus 0 W of x dx. This is x of A, which is, I'm doing this in a kind of a painful way, but you know what I'm doing, right? Integral 0 to 1.4 of 340, that's W of x, x times 340 dx, which turns out to be equal to 340 times 1.4 whole squared over 2, which turns out to be, how much is that? 1666 over 5 Newton meters. You could have done this in a different way. You could have said this is equal to a single force of magnitude equal to the area 340 times 1.4 acting at a distance of 1.4 over 2. You know the centroid of a rectangle, right? 1.4 over 2, and so you can calculate moment equals 340 times 1.4, which is the force, times 1.4 divided by 2, which turns out to be 1666 over 5 Newton meters. You will get exactly the same answer, right? So you can replace this whole thing with a single arrow which represents the total force, and this is where the centroid is, x bar. I don't really care about the y location of the centroid, only the x location, because I only care about the line of action. When we go to 3D, we will look at the y bar and all this stuff. Right now it's only the line of action. That's how it goes. Any questions? Right? This is our method. And your method, if you do this thing, which is first write down the function, calculate F total, calculate moment, and then you have to do some integral, and then you will get the answer. Make sure that your end conditions are right. This is your royal route. Always work. There's nothing more to it. But we can do some shortcuts because this occurs enough number of times. So what I mean by that is, suppose you are given a function that is of a particular form. It looks like a polynomial, ax to the n. Let's look at just one polynomial, ax to the n, and it goes from 0 to L up to this point. Can you see that? So what we are interested in is area of this function and also the moment. It turns out to be very easy. If I want to calculate the area, and if the power n you know, then it is total force, which is the total area, equal to base times height divided by n plus 1, and then the x bar is from the corner, this corner, not this one, this corner, it will be base over n plus 1, sorry, n plus 2, and the moment will be base height squared divided by n plus 1 times n plus 2. Let's make sure it works. So let's say you are a triangular distribution. Okay. Now for a triangle, what's the area? You can see first of all the equation for a straight line is a times x, right? So n equal to 1. So how do I calculate the total area underneath this? It is base times height over 2. Hey, that's exactly this. And if you want to calculate what is the centroid of the triangle, it is base over 3. It's 1/3 of the distance from the corner. Hey, that also works. And if you want to calculate the moment, it is this times that, which will give you base squared height over n plus 1 times n plus 2. The advantage of this is most of the curves we are looking of can be written in as some sequence of a to the n. So what happens if your equation is 3x squared plus 4x cubed? No panic. You just do the same thing, except that you have to do for each of them. You have to calculate F total x bar base. So what happens is the total force will be, treat each of them separately and add up the forces. The total moment will be, treat each of the moments separately and add up the moments. So forces you can add up, moments you can add up, you cannot add the centroids. You can add the forces and you can add the moments. So please do not add the centroids. Now let's look at an example. Here it is. I have two very simple loads and I want to find out what's the net force and net moment at point A. So net force equal to what? Net moment equal to what? And if I have to replace it with a single force, where should I put this force? So let's see. I got 1 and I got 2. Okay, for the first one, F1 will be, let's see, it is base is 5.8 times height is 60 Newton meters. This is base, this is height divided by 0 plus 1. Of course, I am doing it in a silly way, but you know what I mean, right? It's a base times height, which turns out to be, let me make sure I have these numbers. It turns out to be 348 newtons. And x bar 1 turns out to be 5.8 base divided by 0 plus 2, which is 2. Okay, that's x bar 1. Let's do, so this one I have replaced by a single force acting here. I'm going to replace this by a single force acting here. F2 is, if you do the same thing, it is 40 times 4.8, which is 192, and x bar 2 equals, now remember it's half this one from this corner, so it will turn out to be 5.8 plus 4.8 divided by 2. This is the original distance starting from here, there. You see what I mean? Turn out to be 8.2 meters. So I have now replaced it with two forces, 348 newtons, 192 newtons, 2.9, 8.2. So these two things are equivalent, and the net moment will be 348 times 2.9 plus 192 times 8.2 going clockwise like that, which is equal to 12918 divided by 5 Newton meters. So did you see my divide and conquer strategy? I first looked at the two chunks and then I divided. I did each of the chunks separately by using my basically base times height over n plus 1, base over n plus 2, and then base squared height over n plus 1, n plus 2 if you want to do that, or this times that. That's all. This will work as long as your function is reasonably simple. It looks like ax to the n. Let's see if it works all the time. Okay, how to make it work for other situations. So here is a nice one. So your w looks like 1/2 4 minus x whole squared. I'm wondering, hey, wait a minute, it's 4 minus x. It doesn't looks like ax to the n. Hey, wait a minute, but if I look at y like this and x like this, then this function, if let's call this x hat, y hat, it looks like w equals 1/2 x hat to the squared. Hey, we are back in business. So f total equals, the height is 8, so h over 2 plus 1, because n equal to 2, which is, let's see, 4 times 8 divided by 3. Now I make sure that my numbers are right. Is 32 over 3 kilonewton meters. X bar equals, base is 4 divided by n plus 2, 2 plus 2, which is 1 meter from corner. Where's the corner? This is not the corner. This is the right angle corner. Can you see that? So I got to go 1 meter from there. Hey, that was very nice. So I can replace this whole thing with a single force of magnitude 32 over 2 kilonewtons, not kilonewton meters. So 32 over 3 and at a distance of 1 meter, so that the total moment will be 32 over 3 kilonewton meter. So I took this whole thing and I replaced it with a single one like that. And notice I may have to muck around with my axis a little bit to do it. But yet I can calculate net force and net moment. Let's try this one. This looks kind of awkward because it looks like my w of x looks like 3 different functions, right? So I'm going to write w of x looks like x squared plus 3x plus 100. So notice for all of them, base equals 15, base equals to 15, base equal to 15, height equals 15 squared, height equals 3 times 15, height equals 100, n equal to 2, n equal to 1, n equal to 0. So it's pretty easy. F equals BH over 3, which turns out to be 15 times 225 divided by 3, and then plus this one turns out to be 15 times 45 divided by 2 plus 15 times 100 divided by 1. So the total turns out to be 5925 pounds. So moment I'm going to calculate directly, which is b squared h over n plus 1 times n plus 2, because moments are the things that I can add for all of them. So this turns out to be 15 squared times 225 divided by 3 times 4 plus 15 squared times 45 divided by 2 times 3 plus 15 squared times 100 divided by 1 times 2 turns out to be 68625 divided by 4 foot-pounds or pound-feet. Did you see how I did this? if you want to figure out, so the net equivalent force is 5925, the net moment is this, so x bar will be moment divided by force. You can calculate where it is. So here is the net force, 5925 pounds. This distance x bar will be total moment divided by total force, if you want to compute it. Please remember, when you have to do this kind of addition, don't add the centroids, add the moments and add the forces. Okay, those are the things that can be added. Centroids cannot be added. Got this? So this is worked example. Let's do one more. This particular case, it looks kind of strange. So I'm looking at it and I'm saying, okay, notice here is a rectangular distribution. So that is area 1. So this is 1. Here I have a rectangle sitting on a triangle, right? Or a triangle sitting on a rectangle. So this is 50, this is another 50. This is 100 pound-feet. So this is another 50 pound-feet. Okay, so I have a triangle, that's area 2, and then a rectangle, which is area 3. So I'm going to replace this whole thing with one force here, F1, at a distance x1, then F2 at a distance x2, and then F3 at a distance x3. So how much is F1? That's pretty easy. It's a rectangular load. So it looks like 50 times 4, that is 200 pounds. X bar 1 is 4 over 2, that's 2 feet. So that's pretty easy. That's this guy. F2, so this is 1 is a rectangle, 2 is a triangle. So F2, that's this guy. F2 will be 50 times, this length is 6 feet, 6 over 2, base times height over 2, okay, which turns out to be 150 pounds. And then let me make sure that we are on the right track. And then its location, x bar 2 will be 1/3 of the distance from the corner, which turns out to be 6 times 1/3, which is 2 feet from the corner. And then F3 is another rectangle, and this turns out to be 50 times 6, which is 300 pounds. X bar 3 equals half the distance from the corner, 3 feet from corner. Right? So let's draw this well. So I'm going to erase this. I'm going to draw this properly now. So what it looks like is this. F1 is here, and it was 200 pounds at a distance of 2 feet from the corner. 2 feet from the corner. Then F3 is here, and its magnitude is 150 pounds, and it is 2 feet from this corner. It is here, and this is 200 pounds, and it is 3 feet from this corner. Once you have converted it into this, rest of the calculations you can do. You can compute moments and everything, but the basic idea is you can actually systematically break up things into pieces. Okay, with that we are done.